The second type of feedback loop or causal loop that influences a system's behavior is balancing loops. While, as we have seen in the previous video, reinforcing loops drive the system in a given direction, causing growth or decline, balancing loops are the underlying force that stabilizes a system. Let's see a very simplified example of this type of causal relationship. Variable A is the level of hunger that I feel, for example, and variable B is the amount of food that I consume. If the level of hunger increases, the amount of food I consume will increase as well. As we have seen in the previous video, we use an arrow to indicate the direction of causality. In this case, going from hunger to food consumption. And we use a small plus sign to indicate that the variables change in the same direction. Until this point, this is all very similar to what we have discussed. However, as I eat more and more, my level of hunger will start to decrease. Here we can see that the two variables change in the opposite direction. As B, food consumption, increases, A, hunger, decreases. To signal this type of relationship, we usually draw a small minus sign on the arrow depicting the direction of the causal relationship. Since in this example the feedback loop counteracts or opposes the original change, the increase in hunger, we are talking about a balancing loop. Balancing feedback is responsible for reversing or correcting certain processes and for stabilizing a system. These types of feedback loops try to bring a system to a desired state and keep it there. Very common examples for this is how a thermostat works, or how we regulate our body temperature, or the dynamics of predator and prey in a healthy ecosystem. When this type of dynamics works well, we usually do not even notice it. Can you come up with some examples where two system elements are in a balancing type of causal relationship? Try to choose nodes that can be expressed in a way that is quantifiable. Here I do not mean that you need to be able to write a number next to each of the nodes. These variables or nodes can be abstract, like the level of hunger, sadness, happiness, etc. But they do need to be able to increase or decrease. Now let's see another example for a balancing loop where we have more than two elements. In this example, we are going to travel to a field that is full of cows. The more cows we have, the higher will be the grazing intensity. The fewer animals there are on the field, the lower the grazing intensity. Here, the two variables change in the same direction, so we note it with a plus sign. As the grazing intensity increases, the amount of grass on the land decreases. Or, as it decreases, we will have more grass. Here we see that the two variables move in the opposite direction, so we note it with a minus sign. We can see the same type of relationship between the amount of grass available and how many cows die from the cattle, as well as between the number of animals that die and the size of the herd. To determine what type of loop we are talking about, we trace how a change in one variable propagates around the loop. So in this case, we can see that if the number of cows grazing on a field increases, this change will initiate a chain of cause and effect that will ultimately trickle back and start to decrease the amount of the animals, resulting in a balancing or stabilizing causal relationship overall. Over time, the number of animals will slightly fluctuate around a certain equilibrium that is best for that ecosystem. Do you feel that something is off with this example? What do you think is missing? Of course, all our examples presented are highly simplified for the sake of easier understanding. Nevertheless, in order for us to be able to use feedback loops for effectively simulating real-life processes, we need to consider the factor of time. Depending on how long it takes for a change in one factor to cause a change in another, the impacts can be very different. In this example, the amount of grass available on the land does not immediately influence the number of animals that can feed on it. There is a significant time delay. We show time delays when drawing feedback loops and creating system maps by two lines on the arrow where there is a time difference between the cause and effect. So as we have seen, the most important question to ask when we aim to understand the underlying causal relationships in systems is the following. When there is a change in one element of the system, how does another element changes due to this? We can ask this question for each of the links that we have identified. When we find that the chain of changes come back to the initial node of the system, we have found a loop. We can determine how the loop affects the overall system by examining whether the original change results in further change in the same direction or a change in the opposite direction. So it might happen that we see both pluses and minuses around the loop, but at the end the loop amplifies the initial change, resulting in a reinforcing loop. In the next video, we will talk about how connecting loops can help us understand better the underlying system structure.